This problem is asking us to find the true velocity of the airplane relative to the ground. Vector 2 is the velocity of the airplane through the air. And then vector 1, these are really velocity 2, velocity 1, vector v1, is what the air is doing. So the air is moving, we call that wind. And so this is what the air is doing relative to the ground, and this is what the airplane is doing in the air. And we want to just say, okay, what's it doing to the ground? So we basically need to add these two vectors. So I've got my copies here. They're the same orientation. Sorry that I didn't put that like right there. That was my intention. So, all right. So basically, I'm just going to, here's my v2 vector. And I'll move it up a little bit. And then all you do, tip to tail method, is you take your second vector and you bring it around so that its tail is at the tip of the original one. Then here's my resultant vector in waiting, and I bring it so it starts, I'm basically matching there, and then I'm just going to bring this guy to the tip of the second vector, and this is, so this black vector, this black arrow representing the sum of the two vectors, is what the airplane actually is doing relative to the ground. In this problem, we're asked to basically use the tip to tail method to add three vectors, and these are just, we don't even know what kind of vectors these are, but just practice adding them. I've got vector A, I've got vector B, vector C. So what I've done is I've kind of pre-made little copies of them. So this is vector A, and now I'm going to add, I'm going to start with A, excuse me, and then I'm going to add B. No, I'm sorry, I'm going to add C, because it doesn't matter. You can add, just like regular addition, vector addition is commutative. You can go in any, oh, that's weird. Oh, that's what it is. Okay, so there you go, tip to tail. Then my resultant vector, I start at the beginning, the tail of the very first vector, and I draw it to the tip of the tip of the last vector. And then I need to move my little, there it is, that's the resultant vector for vectors A plus B plus C. If you want, try adding them in different orders, and you'll see you'll still get the same result, a vector of this length as an arrow and with that orientation. In the next problem, we are going to use the component method to add vectors A, B, and C together. So I'm going to just make a little table, actually. Oops, let me get, here's vector A, and vector B, and vector C. And I'm just going to say, make a little table of these are the X components and of these vectors, and these are going to be the Y. And actually what I'm going to just do is literally just add them up in this column here. So basically I'm going to go to A, and I'm going to see that 1, 2, 3, 4. So this is abstract math, so no units here, but it's got -4 in the X dimension, and it's up 2, positive 2 going up. So there's 2. For B, I see that it's 3 units wide in the positive direction, and it's 1 unit up in the Y dimension. C is going to have +2, and it's going to have +2 in the Y dimension and -2 in the, sorry, back up, +2 in the X dimension, -2 in the Y dimension. And now, so really the sum, the resultant, is going to just be, add up the X component. So -4 plus 5 is 1 unit in the X dimension. And what do we have? It's going to be the same in the Y dimension. So if I were going to express it the way we're going to, in the component method, the way I do it, I don't use I and J. I'm going to say it's 1 unit in the X dimension, no units because it's just an abstract math thing, plus whatever it is in the Y dimension. There's my little Y hat, and that's going to be 1. So this is the answer. So what if we had done it with the tip to tail method? We would have basically, our vector would have been +1. So our little vector, this would have been R. This would have been the resultant of adding those 3 vectors. In this problem, we're basically doing, here's a little preview, is that oftentimes we're going to have multiple forces acting on an object, and your job will be to determine what we call the net force, which is really just the vector sum of all the forces acting on an object. And we want to do that because we want to, of course, we want to know what's going to happen. So, turns out objects will accelerate in the direction of the net force. So in this case, we have our object is, it's not here on my screen, but I can see there's walls A, B, C, D. And so this object will hit whatever wall that the net force is pointing to. This idea is sum of all the forces. So let's go ahead and add them here. Same, I'm going to use the component method first, and then maybe I'll even do the tip to tail method after that. We'll see. All right, so basically I'm going to create that same table, F1, F2, F3, F4, and this is going to be whatever's going on in the x dimension. This is going to be whatever's going on in the y dimension. And let's get started. F1, I see it's -4 in the x dimension. Okay, these are going to be newtons. I guess I said units matter, so. All right, and this is going to be -1 newton in the y dimension. F2 is over 3, so +3 in the x dimension, and 1, 2, +4 in the y dimension. F3 is -2 in the x dimension, -2 newtons, and it's +3 newtons in the y dimension. 4, there is no y component. It's all in the x dimension, and that's 3 newtons. So there we go. Now we're going to add them up to get our sum of all the forces. So I've got -4 and -2 is -6 newtons, and I got 3 and 3. So there's going to be no force in the x dimension. And then what is it in the y dimension? I've got 7 minus 1 is 6 newtons. So if I was going to show this as a directed line segment, it's going to be up. So it's going to be 6 up. So 1, 2, 3, 4, 5, 6. So if I was going to draw, okay, so it's a little preview. Don't worry about this at all, but this is how we would write it. Sum of all the forces. Right now, just focus on heck, we'll even call it the resultant is, well, I could write 0 with the little x hat. I'm not going to. I'm just going to say it's basically 6 newtons in the y dimension. So this would be our sum of all the forces. Why don't you try it with the tip to tail method, because I don't want to make this too long. You'll get the same result.